Module 5, Network Scalability. There's 2 lessons in this module. Module 1, we'll talk about distributed switch features, and Module 2, we'll talk about distributed switch advanced features. Lesson 1, distributed switch features. After this lesson, you should be able to review the benefits and functions of distributed switches, describe the types of discovery protocols, describe port binding on distributed port groups, describe how VMware vSphere network I/O control enhances performance, describe traffic filtering and marking policy, explain health check, backup and restore a distributed switch configuration, and explain the automatic rollback and recovery of networking configurations. Distributed switches. Distributed switches have the network configuration at the data center level, not at the host level. The distributed switch lives inside of vCenter. Again, it's outside of the ESXi host. Distributed switches are used to simplify administration and centralizing your network configuration. You can add a host to the cluster and uplink it to distributed switch, and you don't have to change anything on the networking because you already have it set up, and it's going to take those properties of the distributed switch. Also, the distributed port groups, they migrate with the clients. So if you're using a distributed port group and you have it enabled for vMotion, all the port statistics and policies that were with that virtual machine get moved over as well. Unlike with the standard switch, each port group lives inside of a standard virtual switch that's inside of that ESXi host. So when you actually have virtual machines and you plug them into a distributed switch, they stay with that port, just like a physical switch. Also, as supporting VLANs, as a standard virtual switch does, distributed switch supports VLANs, but they also support private VLANs. So you can use private VLANs in a private network, so you don't have to worry about duplicating your VLAN IDs across the physical network. Also, network vendors such as Cisco has one. They have a Nexus 1000V. VMware has network appliance APIs to where they can build an appliance, and you can use that switch from a switch vendor to manage, create VLANs, create networks, policies, however you do. Like such, I'll use Cisco for example. The Cisco Nexus 1000V, you can manage that and not even know it's virtual. It works the same way a physical switch does. So VMware has these APIs where vendors can create these appliances that'll hook into that API and take over the management of the distributed virtual switch. Distributed switch architecture. Again, like I said before, the distributed switch lives inside of vCenter. And the best way to think of it, the ports move around. Like as you can see, we have our ports and port groups up here. Well, what happens when we create policies on these ports, like these are for virtual machines, as you can see as this graphic shows, and then here's a management port. Same here, we have some virtual machines, and then here's our vMotion port, and then here's our management port. These policies stay inside this switch. Think of it as a global switch for every virtual machine or every VM kernel we want to create inside of our data center. Now, one thing that will help too, right here, as you can see, and these are the ESXi hosts, host 1 and host 2, we have a hidden virtual switch. They call it the I/O plane. These configurations of these ports, when it's uplinked, we have our uplink port. So as here, each host has 3 uplink ports. These properties and statistics and everything dealing with the port are mirrored down to each host on its I/O plane. Now, the reason that is if we lose vCenter went down, our ESXi host will still perform network functions. In this slide, you can see the differences between a standard switch and a distributed switch. Discovery protocols. We have 2 types of discovery protocols we can run on the distributed virtual switch. We have CDP, which is the Cisco Discovery Protocol, and LLDP, which is Link Layer Discovery Protocol. CDP is proprietary to Cisco, so we'll want to run that when we have our physical NICs hooked up to a Cisco switch. LLDP is vendor neutral, and they started supporting the LLDP protocol in version 5. You can use this protocol. One example I like the best about it is I have an ESXi host and it's plugged into the switch. Well, you go back there and you walk in the data center and you have to find where it's plugged in at to say, oh, it's plugged in to Ethernet 8. So I go back to my office, SSH into the switch, go to Ethernet 8 and make any kind of VLAN or whatever changes I want to. But what's really neat is you can click on the bubble in the distributed switch and it'll show you the LLDP or CDP protocol, and it'll tell you what switch port it's plugged into, so you can go right to that port and take care of it. Just a really neat feature that I like about VMware having these available. Configuring CDP or LLDP. When we enable the protocol, we can either have it in listen, advertise, or both. In listen mode, it's only looking for information that's coming from the physical switches. Advertise means it's only going to send information to the physical switches, and both means it can send and receive. When you have CDP enabled for distributed switch or a standard switch, to view the properties, device ID, software version, and timeout, you can click on this little information bubble, and it'll tell us the adapter, the name of the NIC, and the status. And then also under here, this red circle I'll just go back over. What I was telling you right here, you can see the port ID, which I find very helpful. You can also see the IP address. The IP address might be of the gateway, because you got to remember it's probably in a layer 2 environment at this point. So you'll see the IP address of the gateway. Viewing LLDP information, again, same concept. We'll click on our little information bubbles. We can see the system name, that's the switch name, the VLAN ID it's in, and MAC address, and port description. It'll pull that. Sometimes, like on some of them, you can give it a port description. There's the port ID. So it's a little different than the CDP one, but you can see pretty much the same information. About port binding. Port binding determines how a virtual machine's virtual NIC is assigned to a virtual port. When we select static binding, the port is immediately assigned and reserved for the virtual machine. The port is only disconnected when the virtual machine is removed from the port group. So think about this from the physical side. I've got a network wire plugged in to the network card on my physical host. I'm going to plug it into a physical switch. If I turn that server or host off, that port's still being taken up because it's plugged in. Static binding is what's recommended for general use. When you do select static binding, the default number of ports is set to 8, and it's set to elastic for the port allocation setting. This configuration replaces the dynamic port binding, which is now deprecated. It's been deprecated since ESXi 5.0 and should not be used. The next option we have is ephemeral binding. This is when the port is created and assigned to a virtual machine when the machine is powered on and the NIC is in a connected state. So it's more dynamic. Only going to be used, so think about it as when we turn on this server, we're going to go plug it into the switch from the physical relation. Ephemeral port assignments can be made through ESXi as well as vCenter server. This gives you the flexibility. If vCenter is down, I can still make network changes to ephemeral ports because I can change it at the ESXi host level. Port binding examples. As we can see here, we have a static port binding example. We have 3 ports on the distributed switch port group that are assigned to the first 3 virtual machines that connect to these ports. These ports are permanently locked to the virtual machines. The power state does not matter. If the elastic port allocation is used, then ports are added as needed. So if I add more, it gets added. Dynamic port binding. 3 ports exist on the distributed port group, but 4 virtual machines are powered on. Only 3 out of the 4 machines are connected. When the 4th power is on, it can't connect because we only have 3 groups. Let me go back to this too. Back on the static, same difference. We only have 3. So we'd have to go into the switch and add more ports. Ephemeral port binding lets you have as many ports as you need are available. It's limited only by the maximum for vSphere on your hardware. The power state of the virtual machine does not matter. Ports are created as you connect. So as these virtual machines connect and need network, or their network cards are in a connected state, ports are dynamically allocated to them. About Network I/O Control version 3. Network I/O Control allows us to allocate bandwidth to applications and business processes to resolve situations where we have a lot of network traffic that's competing for the same resource. We can use this to configure bandwidth allocation for virtual machines, management, vMotion, NFS, fault tolerance, iSCSI, the vSphere replication, virtual SAN, and vSphere data protection. You can upgrade Network I/O Control from version 2 to version 3 by upgrading the distributed switch from version 5.1 or 5.5 to version 6. However, this is a disruptive upgrade. Certain functionalities are available only in version 2 and it's removed during the upgrade to version 3. So if you do this upgrade, it's going to take your network offline for a little bit. From version 3, the user-defined resource pools, including all associations between them and existing distributed port groups, are removed. You can preserve certain allocation settings by transferring the shares from the user-defined network resource pools to shares for individual network adapters. So if you want to keep those before you upgrade to version 3, ensure that the upgrade does not greatly affect the bandwidth allocation that's configured for virtual machines that you configured in Network I/O Control version 2. Any existing association between ports and user-defined network resource pools, that's removed. Bandwidth allocation model for system traffic. Again, this is like on the virtual machines, you have shares, or resource pools, sorry, you have shares, reservations, and the limit. The shares can be a number from 1 through 100, and that just affects the priority that the system traffic will have against other traffic types. You can have reservations, which says this virtual, or this port group, or this port, sorry, can have a minimum bandwidth of 100 meg or whatever we specify. Or we can have a limit that says this port can only use X amount of bandwidth. Bandwidth reservation for system traffic. Using network I/O control, we can only reserve no more than 75% of the bandwidth of a physical network adapter. So as you can see here, we have a 10 gigabit adapter. We're only using 75% of it, 7.5 gigabit. Bandwidth allocation for virtual machine traffic. Again, it's the same as it was for the system traffic, but this will be bandwidth allocation we're going to use for virtual machines. Bandwidth aggregation for network resource pools. Again, we can have a network resource pool that represents part of the bandwidth aggregated for a network resource pool across the uplinks of a virtual switch. So we can have a port group, and we can say, okay, it's got this network resource pool A that has 2 gigabit. Port group B has 3 gigabit. Our aggregated VM reservation across these will be 5 gigabit. And again, just like on the standard virtual switch, we can do it per virtual machine. So we can say, okay, this virtual machine right here gets this bandwidth. That's his limit. That's his reservation. Same as this guy. Bandwidth emission control in a vSphere distributed resource scheduler environment. If a bandwidth control or reservation cannot be met on a host, so let's say all 3 of these virtual machines are running here, and it's unable to meet what it needs, reservation can't be met, then that virtual machine will be moved over to this ESXi host so it can get what it needs. And also bandwidth emission control in vSphere HA, same kind of concept. We have a host that fails or is rebooted, and to be booted it has a reservation on it, so we're going to check that reservation. If it can't be met on one host, or host fails, it brings it up on that one. If it can't be met and there was another host and this guy couldn't meet it, it's going to be brought up on the other host. When this ESXi1 comes back up and he can't meet this reservation, then he'll be moved back over to ESXi1. About traffic filtering and marking policy. You can use traffic filtering and marking to create a set of rules for security and QoS tagging of packets that flow through the distributed switch ports. A distributed switch applies rules on traffic at different places in the data stream. It can apply network traffic rules on the data path between the virtual machine network adapter and the distributed port. And it can also apply network traffic between the uplink port and the physical network adapter. So it can do it in 2 places. Creating a network traffic rule. You can define network traffic rules for processing traffic related to virtual machines or to physical adapters. We have an action, and we can choose whether we want to allow, drop, or tag it. The direction we can go, ingress, egress, or both. Again, that's another difference between standard and distributed virtual switches, is standard will only allow us to apply for egress, not ingress, or both. So we can only do it one way going out with a standard switch. We can do both with a distributed switch. We can also do packet classification. We can use a system traffic qualifier, a MAC qualifier, or an IP qualifier. Here's an example that makes use of a system traffic qualifier. They're calling it System Traffic Rule 1. It allows incoming and outgoing virtual traffic. But as you can see, it's only for virtual machine. Again, we put the qualifier in here and we say only virtual machine traffic. Here's the example of a MAC qualifier. And in this rule, we're only going to allow incoming, ingress, traffic from systems on VLAN 32. And then the MAC addresses are in this range. Here we're going to drop all outgoing ICMP packets for any IP address. This is an IP qualifier. As you can see, we're going to drop outbound using egress. The IP qualifier, we want the protocol to be ICMP. If the source address is any, IPv6 or IPv4, and the destination is any, again, version 4, version 6, it's going to match this policy and we're going to drop it. Marking network traffic. We can assign priority tags to the traffic that has higher networking requirements for more bandwidth, low latency. It's the same as we were doing with the IP qualifiers. We can say for virtual machines by MAC address, by an IP address, same thing going on, but what we're going to do is we're going to tag it and then we're going to give it a cost of service value and a DSCP value. The values are 0 through 7 for the cost of service tag. It can be from 0 through 63 on the DSCP tag. Here's an example of marking network traffic. We're going to tag this traffic and give it a DSCP value of 26 on the inbound. We want the protocol to be UDP 5060, and here's the source address it'll be coming from. This whole subnet, because we got this prefix link, and if the destination matches anything. So this example, I'm just reading into a little more. This would be a voice over IP application. Again, 5060 UDP, that's it. And my network from my VoIP must be on that subnet. It's a Class C subnet. If it's going anywhere and it hits inside this virtual switch, we're going to tag it and give it a DSCP value of 26. vSphere distributed switch health check. This is a health check that helps you identify and troubleshoot configuration errors that could be in the distributed switch. It regularly examines certain settings on the distributed switch and physical switches to identify common configuration errors, such as we could have mismatched VLAN trunks between the physical switch and the distributed switch, mismatched MTU settings, mismatched virtual switch teaming policies, or for the physical switch, or port channels to the virtual switch. Here's an example of a health check. We have two ESXi hosts that use one distributed switch with two port groups. So on this host, we have a port group. Our VLAN is 10 and our MTU is 9,000. Our physical switch has a VLAN of 10 and an MTU of 9,000. On this other ESXi host, VLAN of 20, MTU of 9,000, and our team is using port hash. Our physical switch has a VLAN of 10, MTU of 1,500, and no team assignment. So again, we'll get a health check warning on this, and it'll throw up an alert on the health check that just says we have mismatched VLANs and we have mismatched MTU, and our teaming policy isn't consistent. We can enable these health checks by going into the Manage tab of the virtual switch, going to the Settings sub-tab, clicking on Health Check, and we'll edit the health check, and we can just on the drop down either enable or disable VLAN and MTU health check. We can monitor health check results by clicking on the distributed switch, monitor tab, and then this health sub tab, and we'll see our host right here, and then we can see the VLAN, MTU, and teaming health statuses. And then right here, if there's any problems, it'll tell us the details. You can back up and restore the configuration of a distributed switch, distributed port group, and the uplink ports for deployment, rollback, and sharing purposes. The following operations are supported. You can back it up to disk. You can restore the switch and port group from a backup. You can create a new switch or port group from the backup, or you can revert to a previous port group configuration after changes are made. You perform these operations by using the export, import, and restore functions that's available for distributed switches. To export a distributed switch configuration, it allows you to make a backup of it. You can use it as a template for distributed switches, and you can create a revision control system for your distributed switch configuration. So periodically you can export it and save it just like you would configs of a router or a switch. Once you've exported a switch configuration, you can restore it or import it. A restore resets the configuration of an existing distributed switch from the exported config file. So you'd already have to have it existing to restore it. You would restore and it would overwrite one that's already there, because you'd have to restore to that distributed switch. Importing creates a new distributed switch from the exported config file. You can restore and reset a distributed switch that has become corrupted. You can import to create a new distributed switch. For example, if you wanted to import it into a new vCenter server you were setting up. Rollback and recovery of the management network. Rollback prevents the accidental misconfiguration and loss of connectivity to vCenter server by rolling back to the previous valid management network configuration. By default, rollback is enabled, and rollback provides the following options to recover from management network misconfigurations. Automatic rollback if the misconfiguration is detected, and direct connection user interface to recover the management network. By rolling back configuration changes, vSphere protects hosts from losing connection to the vCenter server that's due to misconfiguration of the management network. Updates that'll trigger a rollback, a host level rollback. This is triggered when there's a change in the host network configurations, like you change the physical NIC speed, you change the MTU, or you change the IP address. Distributed switch rollback. This occurs if the user updates distributed switch related objects, such as a port group or a distributed port. Again, rollback's enabled by default. If you want to disable it, you can go to the Manage tab of the vCenter server, go to the Settings sub-tab, click on Advanced Settings, and you'll look for a property called, you can just do a search like they're doing here in the graphic for rollback up at the top right. but you'll look for config.vpxd.network.rollback and you'll make that value false. If rollback is disabled, then the direct console user interface, it provides an easy way for the user to connect directly to the host, and you can fix the distributed switch properties. Again, you'll go down the network restore options, restore VDS, and you can say restore to default blocked setting, or you can restore to default teaming policy, and it'll get you back to where you can get connectivity and make your changes. Again, you should be able to review the benefits and functions of distributed switches, describe the types of discovery protocols, describe port binding on distributed port groups, describe how network I/O control enhances performance, describe traffic filtering and marking policy, explain the health check, backup and restore distributed switch config, and explain the automatic rollback and recovery of network configurations.